Hello students, welcome to chemistry. Yes, I got all my hair shaved off. It's completely gone. It's a whole new look, kind of refreshing actually. So actually my daughter cut my hair like this, so I think she did a good job. When I was young, a long time ago, I had a glorious lion's mane of wavy locks. My hair was beautiful.
And most handsome.
But I've gone bald. What can I do about it? So I thought, let me just shave all the hair off. The problem with being bald is that when your hair grows, it kind of grows out and it starts to look bad. So I just shaved all my hair off since I can't go to the barber because of social distancing. So this is my new look for a while. I think it makes me look like Lex Luthor.
Lex Luthor, the greatest criminal mind of our time.
Well, Superman is a guy from another planet who has all these superpowers. He has super strength and he can shoot lasers out of his eyes for some reason. But Lex Luthor, he has no superpowers whatsoever. The reason he's such an enemy, such a powerful enemy to Superman, isn't because he has some superpower. It's simply because he knows a lot about science. He knows a lot about chemistry, he knows a lot about geology, and that makes him a powerful person. Just another testimony to the power of an education. Anyway, now that I got this new haircut, I want to, dress really nice. I think if I don't do that, it can make me look like a real tough guy, which is a look I'm not really going for. So I'm going to just start, dressing a little bit nicer from now on, now that I got this new haircut. All right, well, I noticed some of you are not turning in recent assignments. Make sure you fix that. I need you to turn those in, even if they're late. Make sure they're turned in. I think some rumors are going around that the grades don't count anymore and school doesn't count. And I think that's a really wrong attitude. To those people that are saying negative things about online learning, I just have this to say.
Bafflation.
All right, so let's make sure that we're serious, we're doing quality work, and I'm working hard to educate you, but I shouldn't be working harder on your education than you are. All of this is really for you. Your education is for you so that you can have a great future, so that you can have as many options as possible. So I'm going to work hard to get you to a good place in the future, but you have to work even harder. So make sure you are dedicated to doing good work. All right, and in that spirit, let's look at the opening. A quantity of iron is reacted with a quantity of dioxygen, and that yields iron 3 oxide. Please remember that iron 3 oxide is Fe2O3. How many moles of dioxygen are needed to make 4 moles of iron 3 oxide? I haven't specifically told you how to solve a problem like this, but pause the video, take a few minutes, see if you can figure it out. Maybe your past knowledge of math will help you solve this problem. If not, of course, I'm going to walk you through it. I will help you out. Please pause the video now and give it a good try. Okay, we're back. A quantity of iron is reacted with a quantity of dioxygen, and that yields iron 3 oxide. So how many moles of dioxygen are needed to make 4 moles of iron 3 oxide? Well, the first thing we need to do to solve it, you must find the molar ratio. You find the molar ratio by balancing the chemical equation. So we have the chemical equation in words. Now we need to translate that to a formula. So we're taking a quantity of iron, I'm going to leave a blank because we don't know the quantity, a quantity of dioxygen, and we're going to make iron 3 oxide. So the first thing we need to do is balance the chemical equation. We have just two elements, iron and oxygen, as our reactants. We have iron and oxygen in our product. Fe, we have 1. Dioxygen is going to be 2. We have 2 irons here and 3 oxygens here. Okay, and how do we balance that? Let's do something with this 3. Let's get it to be an even number. We're going to put a 2 here. That would turn this into a 4. That would turn this into a 6. You've seen this problem before, haven't you? Earlier this week. All right, so we need this iron to be a 4. Well, that's easy to do. And we need this oxygen to be a 6. That's pretty easy as well. And look at this. We added the coefficients of 4, 3, and 2. We would say that this chemical equation has a molar ratio of 4 to 3 to 2. That's wonderful. Maybe you don't need 2 moles of iron 3 oxide. Maybe you need 2 million moles of it. Well, if I'm going to multiply this number by 1,000,000 to get 2 million, then every number in the ratio gets multiplied also. So actually, if I needed 2 million moles of iron 3 oxide, I'd need 3 million moles of dioxygen. I would need 4 million moles of iron. If I'm going to multiply this number by 1,000,000, I'm going to multiply this number by 1,000,000 and this number by 1,000,000. That's the wonderful thing about molar ratios. It allows you to calculate any quantity that you want. So we just balance this chemical equation. We have a molar ratio of 4 to 3 to 2. So the question asks, what if we want to produce 4 moles of iron 3 oxide? So to produce 4 moles, we just have to double this number. And if we're going to double this number, we have to double all the numbers in the ratio. And so this 4 becomes an 8, this 3 becomes a 6, and this 2 was a 4. So we have a new molar ratio of 8 to 6 to 4. Let's look at the question one more time. How many moles of dioxygen are needed to make 4 moles of iron 3 oxide? Well, the answer is 6 moles. The answer is 6 moles because we got the 6 from right there. If it asked how much iron I needed, the answer is 8 moles. 8 moles of iron, 6 moles of dioxygen produce 4 moles of iron 3 oxide. That's how you do that kind of problem. Now, what have we been doing all week? Stoichiometry. Take a look at the way that's spelled. It has an OI and it has an IO. That's how you remember how to spell it. Stoichiometry is the quantitative relationship of reactants and products in a chemical equation. Hopefully by this time, after working all week, you are getting good at stoichiometry. If not, keep practicing. The wonderful thing about education is that we make difficult tasks simpler and easier, and sometimes we even make difficult tasks easy. All right, here's another problem. 10 moles of dihydrogen are reacted with dioxygen to make water. How many moles of dioxygen will be needed to make water with no residual products? That means no leftovers. Okay, I'm going to ask you to pause the video and see if you can solve this. When you have the answer or you've just given up, I want you to unpause the video, but give it a good try. Okay, we're back. Did you pause the video and solve it? All right, so there's 2 ways to solve this. One is to find the molar ratio, but yeah, well, let's look at that method first. Let's get the molar ratio. So we have hydrogen and oxygen on this side. We're going to have hydrogen and oxygen on this side. And we have 2 atoms, or 2 moles, 2 atoms of hydrogen on this side, 2 atoms of oxygen on this side, 2 hydrogens here, but only 1 oxygen here. So let's put a 2 here to get that odd number to be even. This becomes a 4. This becomes a 2. And now hydrogen's not balanced. We can put a 2 here. And let's see here. Ladies and gentlemen, we have just balanced the chemical equation. The molar ratio is 2 to 1 to 2. Okay? And then it said how many moles, let's look at the problem again. How many moles of dioxygen will be needed to make water? To make, 10 moles of dihydrogen are reacted with dioxygen. So if we have 10 moles of dihydrogen, so this 2 becomes a 10. And to do that, we had to multiply by 5. We did 2 times 5 to get 10. That means we're also going to multiply this by 5 and multiply this by 5. Whatever you change to one part of the ratio, you have to change to all of the ratio. So what's 1 times 5? It's 5. What's 2 times 5? It's 10. So it looks like it takes 2 moles of dihydrogen and 1 mole of dioxygen to make 2 moles of water, but it also takes 10 moles of dihydrogen and 5 moles of dioxygen to make 10 moles of water. Let's go back to the problem, and here's another way to solve it. It said 10 moles of dihydrogen, so you can just plug that into the formula and then balance the chemical equation with a 10. That's another way to do it. So we need to get this 2 to be a 10. We can put a 5 right here, and that, or we'd put a 10 right there, I mean, and that would do it. So with a molar ratio of 10, 5, and 10, we have a balanced chemical equation, and we see here that the answer is 5 moles of dioxygen is needed. So I just showed you 2 different ways to solve the problem. You don't need to know both ways. Pick a way that you like best, and just be able to supply the answers when you need it for a quiz, for a test, or when you get a job working in the chemical industry. All right, here's another problem. If 2 moles of Fe2O3, iron 3 oxide, are reacted with 3 moles of carbon, how much iron will be produced? How much carbon dioxide will be produced? Well, this isn't a made-up problem. This is one of the ways they produce pure iron. You need to get some iron oxide, which is rusty iron, and you need to get rid of all the oxygen so it's no longer rusty. So they do that by getting the oxygen to bond with carbon. So this is something that's really done at places that process iron. This is an important chemical formula to industry. So pause the video, see if you can solve it, and then I'll show you how to do it. Okay, we're back. So the first thing you need to do is translate it into a chemical equation. We said 2 moles of iron 3 oxide plus 3 moles of carbon. That's going to yield a certain quantity of iron, which we're going to sell to factories, and a certain amount of carbon dioxide, which we're just going to release into the atmosphere with a smokestack. And people are going to get mad at us because carbon dioxide is a greenhouse gas and we're contributing to global warming. This is one of the problems. When you produce pure iron, you contribute to greenhouse gases. You can see that right in the formula. So knowing chemical formulas also allows you to be more environmentally responsible. You can be a more powerful environmental activist, or you can have a more responsible plant that produces pure iron. Anyway, let's balance the chemical equation. Looks like we have 2 times 2 is 4 irons here. 2 times 3 is 6 oxygens and then 3 carbons. On this side, we're going to figure out those quantities. And if you balance the chemical equation, you realize this quantity is going to be 4 and this quantity is going to be 3. So 4 moles of iron and 3 moles of carbon dioxide are produced. Okay, did you get that right? I hope so. If not, watch this video again, or let's just do another practice problem. How about that? All right, if 80 moles of aluminum are reacted with 60 moles of dioxygen, how much aluminum 3 oxide will be produced? Okay, pause the video and see if you can figure that out. Okay, we're back. Did something familiar did something about that problem look familiar to you? Actually, it should be the same molar ratio as earlier when we were talking about iron 3 oxide. So a lot of these molar ratios actually are the same. So you start to recognize patterns when you do a lot of these. Anyway, I'm going to solve it the new way. I'm going to put in the 80, I'm going to put in the 60, and I'm going to do a inventory list. So we have 80 aluminums here, 120 oxygens here, and we only have 2 aluminums here and 3 oxygens here. So I need a coefficient here that's going to turn 2 into an 80. What's 80 divided by 2? 80 divided by 2 is 40. So that's it. 40 times 3 is 120. That's what we wanted here. And 40 times 2 is 80. And that balances the chemical ratio. So what's the molar ratio? You can reduce the numbers in a molar ratio by dividing by the same number. So we have a molar ratio of 80, 60, 40. But if we want to reduce that, it looks like we can divide everything by 10. And we get 8, 6, and 4. But we can further divide that by 2. So you can divide this number, this number, and this number by 20. And that would give us a molar ratio of 4 and 3 and 2. So the molar ratio for combining aluminum and dioxygen to form aluminum 3 oxide is 4, 3, 2. That is how you find molar ratios, and even more importantly, that is how you use molar ratios in chemistry, in industry, and even in the environmental sciences. The end.